soybean breeding program at the University of Nebraska has been supported for over 30 years by the Nebraska soybean producers through the Nebraska Soybean Board. So I really want to thank and acknowledge the Nebraska Soybean Board for their tremendous support and ongoing long-term support. And that makes a big difference for the kind of work that we can do and the long-term objectives and progress that we can make with that kind of support. So thank you. I'm George Graff, soybean breeder at the University of Nebraska in the Department of Agronomy and Horticulture. On this tour, we're going to go through the sequence of the breeding program. And we're in the crossing block right now where it all begins, where we have developed a plan for the crosses we want to make based on the different objectives. And the main objectives in our breeding program are improving yield or productivity for the soybean farmer. And so yield is the number one objective. Along with yield, soybeans need good compositional quality, so we pay attention to the protein and oil concentration in the seed for processors and end users, and also the quality of the protein and the quality of the oil, so amino acid composition for protein quality and fatty acid composition for oil quality. Soybean is the leading vegetable oil in the world, and it's the number one vegetable protein source as well. So it's a really important crop. So some of the objectives, like I said, are yield, and then we need to protect that yield. So we work with resistance or tolerance to different kinds of stresses, biotic stresses, which are caused by biological organisms, pathogens, fungal diseases, bacterial diseases, or insects. And so some of those things are part of the objectives that we work on in the breeding program. And we'll see an example of working with a new emerging insect pest when we a little later in the tour with Dr. Justin McMeekin working on a soybean gall midge. And then the last thing, like I said, we have yield and we have to protect that yield, and then we have specific objectives for quality of the seed. And so we'll also hear about an example about breeding for increased protein content in the seed. So one example of a breeding objective that we're working on this summer in the crossing block is water productivity. And that's really important to especially Nebraska producers, but to all producers, because water productivity refers to the yield per unit of effective water that the plants receive during the season. And so what we see is differential response to water by soybean genotypes. And we've identified through research and a recently completed PhD project, different lines in our program that have significantly better, greater water productivity than others. And so, for example, in Nebraska for irrigated producers, that means we could save tremendous amounts, 10% or maybe more, with good use and stewardship of the irrigation water. So we could get equal or better yield with better management of the water according to the way these soybeans respond. And it's also important for dryland or rain-fed production systems because when the rain comes during the season, those plants with greater water productivity can take advantage of that water that comes and yield more, provide more yield per unit water than those that are less efficient water users. So we're making some crosses on between parent lines that we have identified with the best water productivity, and we're not going to go over a crossing example, but these flowers that are open, we would be using them as pollen parents, as males in the cross, and then the female on a different parent that we want to cross to would be a bud that we identify that's almost ready to open, but it'll open the next day. And then we make the cross and tag that particular cross, clean out the other flowers from the node, and we can come back at the end of the season and harvest those new hybrid pods. So that creation of new genetic variability, bringing together traits from different parents that are going to hopefully provide progeny that exceed the level of the parents, that's the beginning of the whole breeding process. So the next step in the breeding process after crossing is, for soybeans, we need to inbreed 3 or 4 generations. And for us, that happens in both in Nebraska environments and in our winter nurseries in Puerto Rico and Chile. And again, the Nebraska Soybean Board supports our research and development efforts in the winter nursery areas as well. So in this case, the crosses we made in the crossing block this summer will go to Puerto Rico as F1 plants and will produce F2 seed, and then they'll go through the inbreeding sequence. Our main sequence involves crossing in Puerto Rico in the winter, so we use lighted areas in Puerto Rico to develop the crossing block. Crosses are made in February and March, and the F1 plants come back here for the summer. Then the F2 seeds are harvested and they go through 2 more generations in Puerto Rico from late September through the following May, and then they come back here for planting. So what you see in this field is F4 plants, and we might have 500, anywhere from 400 to 600 or 800 plants in a population. The population comes from the cross that we made. And what we do here is harvest every individual plant based on maturity, so we can separate it in the progeny rows. But each plant in this field of populations from our previous crosses will get harvested individually, threshed individually, and then each of those plants produces a single row in the field, and that's the progeny rows that we're going to see at Mead when we go there for the tour. So there's a field of about 30,000 progeny rows. Actually, we evaluate progeny rows both here in Nebraska environments and about 15,000 progeny rows each year in our 2 Chile environments for the winter nursery. The progeny rows. Each row comes from a single plant that we harvested from those populations, F4 or F5 populations that we have in the field from crosses we made a year ago. So this is the first stage first time we'll see a potential new line in a field. So each row is now an inbred line, and it maintains its identity from here on through the program. The next stage from here is yield testing. In our program, we don't really do yield testing in progeny rows. It's for evaluation visually. We do take some other data, developmental data and things, but we have about 30,000 progeny rows a year in this program, and then cut that down to go into the yield tests in the next 3 to 5 years for variety development. So this is a yield test field. We have about 3,000 yield test plots in this field. This is the next stage after the progeny rows, and we have yield tests here and at about 7 other locations in a given year, or for the regional tests up to 15 locations. So we get a lot of good data on the preliminary and advanced yield tests and make decisions on what gets advanced to become to the next stage to become a new variety. These are increase plots. These varieties have made it through all our initial testing, and they're entering into regional tests, so they have the potential to become new varieties. We have about 35 or 40 increase plots here. They're in groups of 4 rows, about 180 feet long, and these get purified. Their first stage of purification before they go into purification rows, which we'll see next. This is a purification block. This is the last stage in development before the variety gets released. So these lines in these purification blocks have made it all the way through our regional testing and have performed consistently across multiple environments. We know they have stable and consistent performance, and they're set to become new varieties that farmers will grow. So this purification block is checked for purity in every plot, for flower, for pubescence color, growth type, and we eliminate anything that's not uniform with all the other plots. Then these are harvested in bulk, and that is the parent seed that becomes the new variety.